In this video, we're going to look at vectors and their components, and our objectives here are to add vectors by drawing, subtract vectors from one another, calculate the components of a vector in a given coordinate system, given the components of the vector, be able to draw the resultant vector and determine its orientation, and then convert angles between degrees and radians. The reason we have vectors is physics deals with quantities that have both magnitude and direction. And you may remember from your previous physics courses what quantities are vectors and what are scalars. And remember, a vector is a mathematical object with both size and direction. Some examples of vectors are position, velocity, and acceleration. Those are kinematic quantities that both have a magnitude and a direction. On the other hand, a scalar is a quantity that does not have a direction. It only has a magnitude, such as time, temperature, energy, mass. For all of those quantities, we only care about a number or the magnitude of that quantity. Let's think back to a displacement vector. And if you remember what displacement is a change in position. And so if we have a particle that changes position from point A to point B, we can signify this change in position by using an arrow. And that arrow tells us a length, which is the magnitude, and a direction, or the orientation of the change in position. And if we notice the figure over here, all three of these arrows have the same magnitude and direction. Now we can say they have the same magnitude because they have the same length. We can measure all three respective lengths and see that they're equivalent. And they have the same direction because of their orientation. If you look at the angle with the horizon for all of these, they're the same. And you can also tell that by all three of these arrows are parallel to each other. So therefore, they have the same direction and they're pointing in the same orientation. And in part B, we see that all three of these paths, it doesn't matter which path we take, if we take a linear path or a convoluted path, all result in the same change in position, which is the displacement. Therefore, the displacement vector for all three of these paths is going to be the same because they have the same change in position. So say we would like to add two vector quantities together. Well, this process is called a vector sum, and the resultant of a vector sum is the result when you add two or more vectors together. And so continuing with our displacement example, this would be represented by two displacements. What is the net displacement? So if you go from A to B to C, what is your overall displacement from A to C? This idea of vector sum is nothing new. However, something that may be new to you is this notation, vector notation. And we signify that a quantity is a vector by having an arrow on top of it. So if we want to say the displacement vector S, we have an S with an arrow on top of the S to signify that it has both a magnitude and a direction. Typically we have an algebraic symbol or a variable to represent a quantity, but we signify with an arrow that this quantity has both magnitude and direction. And so the vector S is the sum of both A and B. This can be shown graphically if we draw vector A. Since S is the sum of A and B, if we draw vector A, and then from the tip of A we draw vector B. And so this is called tip to tail method. And so we draw those two vectors, and then the result from A to that final stopping point is going to be our resultant vector S. Just like the addition of algebraic quantities, there's a commutative property. Well, there's also a commutative property of vector addition. And so what that tells us is that if we have A plus B, that's the same thing as taking B plus A. And so what this tells us is in our graph, if we drew A and then drew B, we would end up at the same point if we were to first draw B and then from B draw A. It gives us the same resulting displacement. Likewise, there's also an associative property of vector addition if we have three vectors that we want to add together and find their total sum. We can add the first two and then take that resulting vector and add it with the third, or take the last two, take that resulting vector and add it with the first. Either way, we still end up with the same resultant, and the graphs below help illustrate that. When we see a negative sign in front of a vector, that reverses the orientation by 180 degrees, or by pi radians. And so, just like in algebra we have additive inverses, well, vectors also have additive inverses, and so vector b plus a negative vector b is going to be 0. That definition still holds true. But what does that mean when we have a negative vector b? Well, if vector b is right here and it's moving up and to the left, well, negative b is going to be parallel to that, but it's going to move down and to the right. So it's the same magnitude, just opposite direction. The direction is off by 180 degrees. And so this is useful in that if some vector d is defined as the difference between a and b, we can then draw vector a, and then instead of drawing vector b off this way, we can take negative b in this direction, and then we can see the resulting vector d. These rules hold true for all vectors, whether it's displacement, velocity, acceleration, whatever it may be. All vectors act the same. One thing you have to keep in mind, though, is we can only add like vectors together. Just like we can only add like terms in algebra, we can't add a measurement of distance plus a measurement of velocity. That just doesn't make sense. Units don't check out. Those vectors cannot be added. We can only add the same vectors. And so I want you to try this checkpoint here and see that if the magnitude of a displacement, vector a and b, are 3 meters and 4 meters respectively, and vector c is the vector sum of a and b, I want you to consider the various orientations that gives the maximum possible magnitude of c and the minimum possible magnitude of c. So pause the video, think of those, what's going to make the max, what's going to make the min, write it down, and then play the video to check your answer. Okay, so the maximum value for c that we could have with these two vectors is if the two vectors are in the same direction. And if they have the same orientation, then we simply add their magnitudes together and we get 3 plus 4 is 7. So that would look something like a is 3 and then b is 4, and so vector c is 7. Now the smallest that we could have is if we have 4 in one direction and then 3 in the other direction, and we would get a magnitude of 1. Now you may be asking, well, why couldn't we just have 3 minus 4 to give us a negative 1? Well, remember, that negative there is telling us the direction. So the magnitude of this vector is still just 1, it just has the opposite direction as this vector here. So using the graphs and the drawings, great and all to get a mental picture of what these vectors look like, but it kind of gets tough when we want to actually do things mathematically. So we get around that by breaking vectors up into their components, and we say that there's a horizontal component and a vertical component, typically an x component and a y component. It does not have to always be x and y, but that is a traditional conventional choice. This is where we do need to pay attention to the positive and negative signs here, because a component can either be positive or negative along its axis. So having a vector with a component in the positive y direction we know is up, whereas the negative y direction is going to be down. And likewise, we have positive x to the right, negative x to the left. These components do not change if the vector is shifted, if it's moved from one location to another, as long as it is not rotated. Once you rotate a vector, you then change the components of the vector. Rotating it may shift more of the magnitude in one of the directions, either the x or the y direction. Mathematically, we can break down a vector into its components by just taking the magnitude of the vector times cosine of the angle and that gives us the x component, and the magnitude of the vector times sine of the angle, that gives us the y component. Here's the very important part of that, though. That is only the case when the angle theta is the angle with the positive x-axis. So we have to go back to, how do we traditionally measure angles? Well, that's from the positive x in the counterclockwise direction. So a positive angle is in the counterclockwise direction away from the positive x-axis. If you're given an angle other than an angle measured from the positive x, then you have to convert it, find coterminal angles, whatever you need to do to get it in terms of the angle off of the positive x-axis. When given the components, we can find the magnitude and the direction of the resulting vector by these two formulas here. First, we use Pythag to get the magnitude. We just square both of the components, add them together, take the square root, and we can use arctangent of the y component over the x component to find the angle. Remember, that angle gives you an angle off of the x-axis. And so therefore, components fully define a vector. So just having a component, that completely defines a vector, because we can then find its magnitude and direction. If we want to talk about a vector in 3 dimensions, we're going to need to have another component to describe the vector. So using a Cartesian coordinate system, we would need not only an x and y component, but also a z component. Now this over here, the a theta phi, well, that's talking about polar coordinates, and simply a is the distance from the origin, theta is the angle off of the xy, in the xy plane, the angle off of the x-axis, and phi is the angle off of the z-axis. We'll talk more about polar coordinates later, but for right now you can just know that that gives you the 3 components that you would need. Now let's look down at this checkpoint 2 here and talk through what we're seeing. And we're seeing 6 different graphs that all have components and a resulting vector. And we want to know which one of these actually has a correct depiction of 2 components, an x and a y component, and its resulting vector A. If we look at these graphs, graphs C, D, and F all have the proper components. Now, why can you tell that? Well, if you look at the orientation of A, it's down and to the left. So that means we need to have a down vector in the y direction and a left vector in the x direction. And so A is down and to the left. Well, we have a left vector and a down vector. Down and to the left, a left vector and a down vector. And so the difference here is in F we have both components on the respective axes, whereas in C and D we remove one of the components, such as in this one we move the y component. Instead of being on the axis here, we move it over so that way it completes the triangle. F may not be very pleasing in that we don't see a completed triangle, whereas in C and D we do. Now that's possible, you can get the completed triangle, but you have to remember that in order to draw that vector from the tail of one vector to the tip of the other, you need to have the tip-to-tail orientation on the components. For instance, if you look here, in A, we have a tail-to-tail orientation, so that's just like what we have in F, and we just connect those 2 heads, which that's not correct, because what this vector A shows us is that we're going down and to the right, but our components tell us down and to the left, and so those don't agree. That doesn't work. Same thing going on here in B. We have a vector component left and a vector component down, but the resulting vector is up and to the left, so that doesn't work. And the same thing for the vector in E. We have a left vector and a down vector, and it's telling us that we're going up. If we would just change this drawing and go from our starting point to the ending point and have the arrow there, then it would be correct. But since the arrow was going up and to the right, that is not correct. Finally, you need to remember how to convert degrees into radians and radians into degrees. Remember, your factor is 2 pi over 360 or pi over 180, and that converts 40 degrees into 0.7 radians. And remember, radians are just a measure, it's an angle measure. And also with that, you're going to need to remember your three basic trig functions and what they represent in a triangle.